Hello guys, welcome back to Maison African Motives, still on Industrial Electronics N1, June 2022 question paper, which is the one that we have been working on. Now on a continuation from the questions that we had now on question number 3. So in this platform, we are going to quickly rush through the questions and see what we're given. So the first part of question number 3, that is 3.1, we are given here to calculate the resistance of a 1000 meter copper conductor, which has a cross-sectional area of 35 square millimeters, the resistivity of copper being 17.3 times 10 to the power of minus 6 ohm meter. All right, so here we you just need to take our values properly. So this is 3.1. So remember that the resistance is given by rho L over the area, which is the resistivity times the length divided by the cross-sectional area. But in this case, we just need to change one or two things here. The resistivity is fine, 17.3 times 10 to the power of minus 6. That one is not going to change. There is nothing that we can change there. 17.3 times 10 to the exponent of negative 6 times the length. All right, let's check the length. Is it in meters? Our length is in meters, so nothing is going to change. Just going to use the 1000 as it is. That is our length. And the area, if we are to check on our area is given in square millimeters, of which we are supposed to have this in square meters. So whenever you have got a square millimeters, for you to convert to square meters, you multiply by 10 to the exponent of negative 6. Your answer is now in square meters. So that means it is going to be 35 times 10 to the power of minus 6 in meters. All right, so we are going to have 35 times 10 to the exponent of negative 6. So that automatically can give us the resistance. All right, just checking here, we can see that some of the things are just repeating here. Times 10 power minus can cancel. Or if you didn't see that, then you just have to use your calculator direct. 17.3 multiplying by 10 to the exponent of negative 6, whatever that you give, multiply by 1000, divide by 35 times 10 to the exponent of negative 6. So we are going to obtain the resistance of the circuit, which is 494.286. This 7 is going to change 5 into 6. So that is 494.286 in ohms. So that was the total resistance that you're going to have. So knowing your formula and substituting into the formula, that was the concept of the question there. All right, on 3.2, we are given briefly explain the term temperature coefficient of resistance. What is the temperature coefficient of resistance? The temperature coefficient of resistance is the relation between the increase in resistance per degree Celsius increase in temperature at nominal value, usually 0 degrees Celsius. So this is a continuation, guys. Here, the way that it is presented, it can actually confuse someone here. This is actually a continuation that is happening. Okay, so I just hope it is clear. Okay, let me just do this. Let me do this so that I can present what I'm trying to say here. Okay, I'm saying this is a continuation from this point that we have to this point to that point. So it's actually a continuation. So temperature coefficient of resistance is the relation between the increase in resistance per degree Celsius increase in temperature at a nominal value, usually 0 degrees Celsius. Okay, so it's a continuation. Don't make it in point form like that. No. Okay, or it is the effect that a change of temperature has on the resistance of a conductor. It's also a continuation there. So this point to that point, it's a continuation. So you can choose which one is the best from the two that we had. Okay, on 3.3, we are now given make a neat labeled sketch to show how a multimeter could be connected to measure the following: current through the load resistor, then voltage through the load on 3.3. 1. what is the current. So if you are measuring current, remember it's supposed to be in series with the load. That is your ammeter here is the one that you are using to measure the current. So it is connected in series with the load, which is opposite to voltage, which is now connected in parallel. This will be the voltmeter now to measure the voltage. So you're going to have your voltmeter connected in parallel with the load resistor. You have the total voltage by doing that. All right. So that's what we had. Make sure you understand the sketch drawings. Make sure that your drawing is properly presented. Right, on 3.4, we are given that a battery has got an EMF of 8 volts and internal resistance of 0.8 ohms is connected across two resistors in parallel with effective resistances of 10 ohms and 15 ohms respectively. Okay, that's a battery there. So let's see if we can just have a sketch. We've got a battery here. So this battery is actually having its voltage, which is an EMF of 8 volts. So we are given 8 volts there. The internal resistance, so we've got the internal resistance of 0.8 ohms. So this battery is connected across two resistors. There are two resistors which are in parallel. Okay, so we've got two resistors in parallel. That's the first resistor and the second one in parallel. So you just name them R1 and R2. It's fine. Okay, so the first one is 10 ohms and the second one is 15 ohms. So we've got 10 ohms here, we've got 15 ohms. So this is just a sketch of the circuit diagram. So the question is calculate the following 3.41, the total current flowing, the total current flow through the circuit. What will be the total current? As we know that for us to have the total current, definitely we must have the total voltage, which is the total EMF over the total resistance for the circuit. So we are supposed to calculate the total resistance for the circuit. So just like what we had on the question 2, the previous question 2 that we had, is it question 2 was still this same question? Let me check. No, it was question 2, which was on electrical circuits. There we had a combination like this one, whereby we had a parallel, then a series. So for us to have the total resistance, let's start with the parallel part, these two resistors in parallel, so that we can use the formula to calculate the current. So RP is going to be product over sum of the resistors. So that's product over sum, of which we are multiplying R1 to R2 over the sum of R1 and R2. So that's it, product of 10 and 15 over the sum of 10 and 15. We can have the parallel combination in terms of the resistance. All right, so let's see what you're going to have here. That is 10 by 15 over 10 plus 15, 10 plus 15. We've got 6 ohms. So we are going to obtain 6 ohms here. So which means if we are to check what we actually have, this is the parallel, or RP. So our combination was going to look like this at the end. We are going to have that internal resistance and the parallel resistance that we got, which is like this. So this is what we're going to have as our final answer. Our RP being 6 ohms here, and that internal resistance of 0.8 and our E of 8 volts. So as we can see now, to calculate the total resistance of the circuit is the internal resistance that is left and that combination of RP that we got here of 6 ohms. So we're going to add RP. All right, so that's it. R, which is 0.8 plus RP, which is 6, is going to give us 6.8 ohms. So this is the total resistance. But the question is not about the total resistance, it's about the total current in the circuit. So to find this total current now from this combination, we say the total current, that is E over R, that is the total EMF, which is 8 over the total resistance of the circuit, which is 6.8. So that enables to calculate the total current. So let's see what we have from our calculator. 8 divided by 6.8, that's 1, something, 1.764, which is just 1.76. 1,176 amps. This is current. Current is measured in amps. All right. So that was the question, 5 marks. As you can see, it needed you to work on it properly. Well, especially having circuit diagrams, it makes things easier. All right, 3.42, that's the potential difference across the external resistors. Which are the external? Remember, this is the internal resistor. So the external resistors are these two, which is the parallel combination. And in a parallel combination, we can check here that the current that is flowing as our total current here is the same. That is also going to affect the parallel combination. So that means the voltage is going to be taken from current and resistance. That's what you're going to have. So this is 3.42 now. All right, so 3.42, the voltage across the parallel, that is the external. These are the external resistors, the ones that are in parallel. So it is going to be the total current times the total resistance in parallel, which is the total current. We got it here as 1,176 times the total resistance for the parallel combination. In the parallel combination, we got a total resistance here of 6 ohms. So you're going to multiply by 6. So that's what you're going to have here, which is 1,176 times 6. All right, so we have got 7,056 volts. This is volt, so voltage. So measured is measured in volts. If it was power, measured in watts, current measured in amps, and resistance in ohms. So make sure that you know the units of measurement for each and every component that you are calculating. So that's what we had, guys, on question number 3. As we can see, that was our question 3, having a total of 20 marks. So these are the typical questions, and that's how actually they ask these questions. So for you to get used to these questions, you have to work on much question papers, revisions, textbooks, and videos from our YouTube channel. Don't forget also to share our platform to your friends and colleagues so that they also can benefit from this information that we are having as a family. From Mason African Motives, till we meet again.